We have proved this Shearer's lemma. And that's about the size of independent set, large independent set in triangle free graph. And that implies the bound on the range number. So how do you do it? The proof is simple. You just consider n is this number and then show that any triangle free n vertex graph contains an independent set of size p. If there is vertex with degree at least t, then its neighborhood is an independent set. So we are done. Otherwise, we know that its every degree is bounded. Then what? And Schur's lemma says that we have an independent set whose size is at least (-1 times n log d over d. And if you apply t here, then what? N over t log t. And then from here, what you get? This is like bigger than or equal to t if we choose the (-1) term correctly. Okay, and okay. And we can use some inductive argument to actually show that this holds. So how do you do the inductive argument? When you take a vertex, so this is like t grows infinity and s is fixed. If you have a neighborhood, so in the previous one, you simply said that it is triangle free, so this is immediately independent. However, in this case, it is KS free that you consider. So it's not independent set right away, but this is now what? KS minus 1 free. So let's say S is 4. Then this is what? This is K3 free. So you apply the above result. This is triangle free graph. So you apply Shearer's lemma here directly, then you get the independent set. Then replace this part. And then the other part, simply, yeah. So that give you the bounds on the, every degree. And then, yeah, that kind of inductive argument you use to obtain this. And then Komnoshi and Sam already improved this to, better law here. And that's the, best known upper bound. And for best known lower bound, in 1995, Jong-Han Kim proved that the R3T is at least some constant times T squared over log T. Confirming that it is actually height up to multiplicative constant. So this is correct order of magnitude for this Lambda number. And best known bound is by group of groups of people. So Fis, Pontiveros, and Griffiths and Morris in 2021, and independently Bowman and Kibash, they proved that the R3T is at least 1/4 minus 0.1 times T squared log T. So the above upper bound is height up to multiplicative constant at most 4. So that was about this Lambda number 3T. And get back to the Shearer's lemma. So we show that you have a triangle free graph, then you have a large independent set. And okay, then it's natural to ask why this triangle freeness is so special. Can we prove similar thing for other conditions? And there are many such approach. So Lee Roziu in 1996 proved that the same bound holds for C4 free graph. And Shearer, again 1995, proved that the slightly worse bound so there is this additional log D term here for arbitrary KS free graph. Of course, with average degree D. So there is this additional log term, but one natural question is, can we remove this log D term? So it's conjectured that this term would be removed. So for KS free graph or arbitrary S, essentially the same bound will hold with the triangle free graph. But this is still open. And instead of just considering independent set, what could be done is you could consider chromatic number. Johansen in 1996 further proved that the least chromatic number is at most D over log D, holds for, say, triangle free graph. G with the maximum degree at most D. And then Molloy in 2017 improved this further to better constant. So what does it mean? So if you have a chromatic number, so let's say chromatic number at most D over log D, and you just can partition the all n vertex into what? Its many set of independent set. And then if you take one of them which has the largest size, then what? That has size this. So instead of finding one, you can even partition your graph into independent sets of almost optimal size. So that's what they proved. Okay, at least actually this is the row base natural log. So this is essentially same bound. This gives the essentially the same bound with the shear lemma here. Okay, and here again, you can ask why only triangle free graph. Can you do for other graph? In 1999, alone, Ibrahimovic Jakov proved that any graph P with the maximum degree D, where so triangle free graph means that its neighborhood contains no edges. So instead of it contains no edge, it contains small number of edges. It contains at most, say, D square over F edges. It satisfies the chromatic number is at most some constant times T over log F. So if F is say D squared, then it's, let's say if F is say 2 times D squared, then at most half edge means no edges. So that's triangle free case. So if you plug in D squared here, then what? That's T over log D. So essentially this implies like this theorem without least chromatic one. So this is even stronger for least chromatic number, and this is for chromatic number. Okay. And there are many applications of this independence set theory. So another application of this, like finding large independence set. An application of such thing, maybe we can discuss one. One is about sphere packing. So what is sphere packing? Let's say you are on R2 and you want to put the sphere, two-dimensional sphere, so unit circle, unit disk. You want to put it without the overlapping. Sharing boundary is fine. And let's say you put it this way, and this repeats. Then you can consider the fraction of the plane that you have covered. What's that? That's like this picture is repeating it. So you can consider that this is unit sphere. So, unit disk. So let's say its radius is 1. And that's what. So this is pi. And then this is what? 4. So pi over 4 portion is covered. And we can ask whether this is the best part of it. And indeed, there are other ways to do this, like this. And there are many ways. Anyway, so out of them, you could try to find the ones that cover the most fraction of the space. That's very critical question. And you can ask it for RD. So in RD, you consider a collection of unit balls in RD, and you want to put them in a way that their interiors are pairwise disjoint. So what is sphere packing? So sphere packing in dimension D is a collection of unit balls in RD whose interiors are pairwise disjoint. And let's say the famous problem is that determining the, say, theta of D is maximum fraction of RD, this space that is contained in all of the sphere. And this is famous problem. This is known for these 1, 2, 3, 8, 24. And all of the, so 1 and 2 are relatively simple, and the others are all very big problem. So I think it was 100 years old problem that was recently, determined. This was computed using computer, I think. The paper itself is like several hundred pages. And these two results gave the Fields Medal to Biadowski in the recent years. Anyway, so in general, this is very difficult problem. Then we can ask for general B. Then what happened? The upper bound is known. Essentially, this kind of number, 2 to the negative 0.599 some number plus 20. This is what by Kobasiansky and Revenshutey in 1978 and Kwon and Zhao in 2014 improved this by constant factor. On the other hand, what's the lower bound? It's easy to see that this lower bound holds. Why? If you have this is a volume argument. If you have a PR packing, and whenever there is a point that you can add, and you add. So meaning that, okay, there is some space, put another additional one you put. You do that until you cannot. Then what happens? Assuming that you cannot put anything anymore in this space, then what you do is you extend your bore to radius 2. So instead of unit bore, you make the radius twice. Okay, then I claim that every point should be covered. Every point on the plane should be covered. Why? If some point is not covered, then that's at least distant 2 from every center of every sphere. Then there you can put a new sphere whose center is there. Then it will not intersect with any of the other sphere. So if point is not covered, that means there is possibility to put one more sphere, which is not the case because we assume that this is maximal. So once you magnify every sphere by 2, then entire space should be covered. That means before magnifying it, it should cover at least this amount. So once you magnify by 2, then you multiply 2 to the d. The covered area is multiplied by 2 to the d or less. So once it magnify that, then it becomes 1. So original 1 is at least this. And there are several ways to improve this to provide D in front of it. So there are many results. Essentially, I mean, those results of how you do this resembles what Shirach found did. And the current best roll bound is by Campos, Jensen, Fisherland, Afradude. They proved that it is like 1 minus 0, 1 times d log d divided by 2 to the d plus 1. So instead of just multiply d, they show that you can even multiply d and log d. But still, you can see that the lower bound and upper bound are exponentially far. So essentially how they did it is the following. Assume you have a RD, and what you do is you sprinkle points at random. You randomly discretize. And of course, I mean, you have to determine how to do this. And I mean, but somehow you, I mean, sprinkle some random points. So once you have this discretization, and then what you do is you consider graph G on the, I mean, with the vertex set on this point. How? X and Y are adjacent in G if the distance between them is at most 2. That means if we choose one as the center of your sphere, and the other one cannot be a center of your sphere. If both of them are center of sphere, then their distance has to be at least 2 so that the sphere does not intersect, right? So you get this. And then now what? An independent set in G yields a sphere packing. Okay, technically, I mean, we want to do it in infinite space, but you can restrict your attention on the large box, say m by m to 0 to the m, no, let's say negative m to the d box. And then you just do it in there, and then you take the limit m goes to infinity, then you can get the sphere packing. So essentially, you can do this on finite space. And in finite space, you do this, then you get the finite graph. And then once you find the large independent set, that gives you a sphere packing. And then if your independent set is large, then it is also good. And what you can do in here is that in this situation, if you have some vertex u and some vertex b, and then their distance between them is x, then what you can do is when you sprinkle it, you can make sure that the distance between them is like somewhat controlled. There are no case that they are too close. So their distance is somewhat have a lower bound. And what happened is that I mean, okay, before that, what's the neighborhood of u? You can actually compute. So you consider the bore of radius 2 in here, and then you count the number of vertices, number of points in sphere of radius 2 centered at u. And you can show that this number is very concentrated, meaning that the degree of u and degree of v are very similar. because we randomly scatter them. You can compute that with high probability. I mean, this is quite, the degrees are all similar. So this is almost regular. And for two vertexes U and V, what you can show is that you consider the pair here, and then against pair here. Then what you can show is that any points in here are co-neighborhood of this UV. So this is exactly the points in blue area. And what do we know? This radius is 2. This is x. Then what? This part, you can compute this y. This y is actually strictly smaller than 2. Because this is 2, this is x. You just do some Pythagorean theorem or whatever, then you can compute this once x is not too small. If we know the lower bound on x, you can get this upper bound on y, and you can consider the volume of this. Roughly, the volume of this here is 2 to the d times some constant. And the volume of this blue part is what? Y to the d times some constant. So this, for large d, this is exponentially small. So what we can show is that the degrees are large and co-degrees are small. Then what it means? So for each b in this graph, in neighborhood, every vertex here has small degree inside of here. So these are parts. There are not too many edges inside of this neighborhood. Because its degree inside is exactly the co-degree, and that co-degree is exponentially smaller than the size of this. So this is roughly in the setting that's similar to, say, this theorem. Then in that case, I mean, they show that in that case you can find the large independent set in the graph. Roughly their theorem is something like this. So G is n vertex graph with the maximum degree d delta, and every pair of vertices has at most delta over 2 log delta to the say 7 common neighbors. Then they show that the largest independent set has size like this. And then from there, you can deduce the sphere packing density, lower bound. Okay, and the proof of this is kind of resembles the Roder-Nibel method that we have learned in the progressing method course. You can see my lecture on my webpage, or there are many good lectures or lecture notes on the internet about the probability method. Okay, so that was several, discussion on some applications and development on the theory on finding large independent set in a graph. Okay, so next time we will talk about counting independent set. Okay, then I will see you next time. Thank you for listening. I will see you next time.